All right, so as you now see on the screen, our first speaker is Richard Woodard, and he's going to tell us about how inflationary gravitons affect gravitational radiation and force of gravity. So, Richard, please.
Okay, thanks a lot. And let me join all the other speakers in thanking the organizers for setting up this conference and for inviting me to speak at it. I'm a North American, and my colleagues just continually lecture me about the need for more diversity in physics, which always puzzles me because, as you know from the history of science, physics from its beginning has been one of the most diverse of human intellectual endeavors. The research that I'm going to report on today is the result of collaborators from 3 different continents. My graduate student, Lin Tao Tan, who is Chinese, my good friend and colleague, Professor Nick Tsamas from the University of Crete, who is Greek, and excuse me, and in one of the relatively routine ironies of conventional research, Lin Tao is right now in North America, whereas I'm in East Asia. So what I'm going to talk to you about is the effect that inflationary gravitons have on the propagation of other gravitons and on the force of gravity. The physical basis for this is that inflation rips a vast, beyond imagining ensemble of long wavelength gravitons out of the vacuum. That's characterized by the tensor power spectrum, a rough approximation of which is given right there. That's a tree order quantum gravitational effect that I hope will soon be observed. If you write the co-moving energy of these gravitons for one polarization and one wave number k vector, or one wave vector k vector, then the occupation number, if you write that as h bar omega times a half plus n, the n that you get looks like that. So it's characterized in terms of this, in principle, observable quantity. And it goes like 1 over k squared, which tells you that these gravitons are an infrared effect, a long distance effect. That's important because that tells you you can use quantum gravity reliable. And very important, it grows like a squared. Remember, a is growing exponentially rapidly during inflation. So there is a staggeringly large ensemble of these gravitons. They must, at some level, interact with themselves and with other particles. And what we want to do is to study how it is that they change the propagation of other gravitons and of the force of gravity. It tickles me when people come up with these complicated mathematical proofs that allege to show that there can't be any such effect, because this is just routine in other branches of physics. For example, my late University of Florida colleague, the late Professor Stephen Detweiler, is renowned for having suggested that we can use the way gravitational radiation changes the kinematics of photons to detect gravitational radiation, a program that is well underway and I think will soon yield positive results. You can also calculate on flat background, the corrections, the quantum gravitational corrections to the Newtonian potential. I think that calculation was first done by a student of Julian Schwinger in 1970, and there's the result that he got. The way that you study these effects in general is you compute the graviton's self-energy. So you write the full graviton operator as a squared, the scale factor, subtract off the background piece, and what you're left with is the graviton field operator. Kappa squared is the loop counting parameter of quantum gravity. And what you calculate is the one particle irreducible 2-point function for the graviton field. That has a pair of indices at the point x and a pair of indices rho and sigma at the point x prime. You use it to quantum correct the linearized Einstein equations. So this is weak gravity because it's an individual graviton propagating, or the force of gravity. So you just need linearized effects in H rho sigma. This is the classical part, the so-called Lignerovitz operator contracted into the graviton field, and that's the linearized stress tensor, and the quantum correction takes this form. It's the graviton self-energy integrated into a graviton field. And the way you would use this to look at how it is that inflationary gravitons change the propagation of other gravitons is you would set the linearized stress tensor equal to 0, put in h mu nu is equal to exactly the same polarization tensor that you use in flat space, times a time-dependent mode function, times a spatial plane wave factor, and then you would solve for how it is that this guy gets changed by the impact of the quantum correction. If you want to look at corrections to the force of gravity, you would set the linearized stress tensor equal to that of a point mass. Most of that's obvious. The scale factor here is the one thing that comes from the expanding universe. And then you would look at, in a particular gauge, say H00 and the trace part of Hij. Well, let's talk first about how to represent this thing. The graviton self-energy is a bitensor density. That means that it has technically 4 to the 4, 256 different components. It would be mind-numbingly stupid to give a table of all 256 components of it. What you do is instead to simplify it by exploiting the symmetries of cosmology. So the background has homogeneity and isotropy. That means that there are 3 special tensors. Delta mu nu, this would not be present in flat space as a special tensor, but it is a special tensor in cosmology. The spatial part of the Lorentz metric and the spatial part of the derivative operator, the gradient operator. Then you write graviton self-energy as a series of 21 basis tensors, the Ds, the script Ds, acting on scalar functions. I'll tell you what these things are. The Ds are just constructed out of these 3 tensors. And the 21 Ts, it turns out if you use the fact that when you interchange X and X prime, and mu nu and rho sigma, that's called reflection invariance, it turns out that only 14 of the 21 Ts are independent. And I know you were all dying to hear what the Ds, script Ds are. Here's a table of all 21 of them. So for example, D1 is the spatial part of eta mu nu, eta rho sigma. T22 or T21 is just a product of 4 spatial derivatives. The scalar coefficient functions depend on the 2 scale factors. There can be some local terms that depend on delta 4 of x minus x prime, and then non-local terms that depend on the Lorentz invariant inner product between x and x prime. Remember, we're using conformal coordinates, so after you remove the scale factor, the Lorentz invariant inner product can occur between 2 points. So for example, the scalar coefficient function T2, which we'll see is very important for describing gravitational radiation, that takes the form given here. Everything has a factor of kappa squared, 1 factor of the loop counting parameter. And then it has a whole bunch of terms that are proportional to delta 4 of x minus x prime and have a factor of logarithm of a, which remember is growing linearly in co-moving time, and then a bunch of non-local terms. And I've organized these between the ones in green, which are inherited from flat space. They would be present even if you took a equal to 1 and h equal to 0, and the effects which are strongest for cosmology. Those are the ones with the most number of scale factors, the fewest number of derivatives, and the largest numbers of factors of h. So it turns out that even the 14 TIs also are subject to constraints. Those constraints have to do with the symmetries of quantum gravity. So they have to do with vertices, the way it is that gravitons couple to things. So if you take the covariant derivative on one index, you could write that, again, just using general tensor analysis, as a bunch of 3 index script Ds, given right here. There are 10 of them, times scalar coefficient functions S, I, which you can build out of the TIs, and I'll show you what they look like explicitly. The divergence on 2 of them is simple enough that I don't need to use a table. I can just list all the 5 independent tensor coefficients. So there's delta mu 0, delta rho 0, and scalar coefficient functions, the Ri's. Well, what do these things look like? The SIs can all be expressed in terms of the TIs. There's what they look like. You'll see some factors of D there. That's the space-time dimension, because we're doing a dimensionally regulated calculation. The S's, or the R's, which look like there, are given in terms of the S's. The reason that these things are important is because different numbers of gradients acting on the graviton self-energy have to give zero. So matter vertices are linearized stress tensors, and those things must be conserved unless the string theorists have changed something. So what that means is that the divergence on either index group, either on X or X prime, but just one divergence must give zero. If you look at that, that says that each of these 10 S's has to vanish. So that means that the 14 T's that we algebraically independent T's are subject to 10 constraints. That means that there are just 4 independent ones left over. If you were on flat space, that counting would give you 2. We chose T12, T16, T18, and T19. These diagrams here are examples of matter contributions and pure gravity contributions. Graviton vertices are not conserved, but the whole thing is conserved. So if you take the divergence on 2 index groups, you have to get 0. That means that it's not the case that the S's vanish, but the R's have to vanish. So the 14 algebraically independent T's are subject to 5 constraints, and that means that there are 9 things left over. We took those to be the 4 T's that we also use for matter ones, and then the S's are the easiest ways to represent these things, even though those things are themselves combinations of the T's. Okay, so that's how you represent things. An example of what everything looks like once you get done expressing it in terms of the independent ones is how it is that the graviton self-energy depends on T12 and on S4. And these things involve Ricci and Weyl operators, so-called because they're bits and pieces of the linearized Ricci scalar and the linearized Weyl tensor. So if you take this operator, pi mu nu sub a, that's just the spatial transverse projection operator. And that can be used to give a Ricci operator, script r mu nu, which is there. And you can also build a Weyl operator, CAA, given by that. And T12 is just this linearized Weyl operator acting on 1 over del squared of T12. S4 has a more, and notice, by the way, that obeys the divergence on either index group, because the divergence for just the spatial part is just the regular gradient. And this thing is the spatial transverse projector, so any gradient of that vanishes, and it's also traceless. So that's what the dependence on T12 looks like. The S's, which remember are things which are only annihilated when you act on both index groups, have a more complicated structure. They involve typically one of these guys times some other tensor on the other index group. So for example, an RA on X prime times another tensor on X plus then the symmetric combination at R on X plus that same tensor on X prime. Okay, so that's what they all look like. The whole point of doing this is so that we can look at the linearized effective field equations. Remember, those linearized effective field equations take the form of the Lichnerowitz operator plus the quantum correction equals the linearized stress tensor. What does the Lichnerowitz operator look like? Well, if you acted, I won't give it to you in general, but if you specialized a de Sitter background and acted on a linearized graviton, it just takes that form. So it's some second order differential operator acting on the mode function times just the spatial part factors out and the polarization tensor factors out. On the potentials, it's a little bit more complicated, but not too much more complicated. You get 4 independent pieces, the 0, 0, 0i, and ij piece, but they're subject to 2 constraints. So you only need 2 equations. Obviously, you take the simplest equation, the mu 0, the 0i, and the di dj part of that. Okay, so that's what the tree order operator looks like. The tree order solutions of these things are for gravitons, it just takes that form. And if you take the late time limit, which is very relevant, this thing goes to a constant. That's the thing that gives the tensor power spectrum. And then it falls off like 1 over a squared. And interesting effects would be if you change this constant, or even if you change the fall off, the rate of fall off, that would be interesting. The response to a point mass, well, at tree order, it's just a de Siderized version of the stuff you learned as a high school student, the Newtonian potential. So you just take the R and multiply it by A to make it a physical thing. And that's just a de Sitter version of the Newtonian potential. Notice that the so-called gravitational slip, C minus phi, is equal to 0 in classical general relativity, but it's not in general, and it won't be when we include these quantum corrections. So now we get to looking at what the quantum correction part of the equation looks like. So for gravitons, it turns out that it just involves T2. So it turns out all the other structure functions drop out. You just involve T2, and it takes this very simple form right here. And that's why I gave you what T2 looks like. The response to a point mass is these two equations that we chose from the Lichnerowitz part of the operator is equal to these different structure functions integrated up against the C's and the Phi's. Okay, well, at this stage, some of you are probably screaming and saying, wait a minute, what about reality and causality? You know, you've calculated these things. If you calculate these things in Feynman diagrams, you're going to get two bad effects. You're going to get the first kind of effect that you get contributions on this side of the equation that exist for x primes in the future of x. And the second bad effect you're going to get is that these coefficients t will be imaginary. That's all solved by using the Schwinger-Keldysh effective field equations rather than the true effective field, rather than the Feynman effective field equations. And that's what you would use if you wanted to take true expectation values as opposed to in-out amplitudes. The derivation of that is a little bit complicated. I won't go through it, but the rules are very, very simple. You just replace each ti that would have occurred in the in-out formalism by a ti plus plus and a ti plus minus, where the plus minuses are just those things. You'll notice that they agree when eta is less, when eta is greater than eta prime. So there's exact cancellation if you ever are in the future. They disagree, they're complex conjugates otherwise, and the fact that they're complex conjugates is what cancels the imaginary part as well. So this is all real. It's non-local, it's intrinsically non-local, but it is real and causal, very important. If you look at what happens to the contribution from a not from gravitons, but from matter correction to the graviton self-energy from a loop of massless minimally coupled scalars. That was So-Yeon Park's thesis project, which was done in 2011, and the workup of that to see what the effect is on the potentials was done by So-Yeon Park and Tomislav Prokopets and myself in 2015. By the way, there is no effect, just like in flat space, there's no change to the graviton mode function. The effect on the potentials is there, and it takes the form of a piece which is just a de Siderized version of that part that Schwinger's student Radkowski got way back in 1970, plus an intrinsically de Sitter part that goes like GH squared. And let's comment a little bit about that. The Newtonian part, or the flat space part, is always going to be very not so important. The reason why is just dimensional analysis. Corrections, one loop corrections, have to go by the loop, like the loop counting parameter, which is the Planck length squared, and hence they have to be divided by a length squared. And that means that they're only going to become significant when you're very close to the point mass, much closer than you could actually get when you take into account quantum, other quantum field theory effects. In cosmology, you've got another dimensionful parameter, namely h squared. So you can have the product gh squared. That's what the intrinsic cosmological effects look like. And because you continually dump more and more particles, you can also expect secular effects, effects that grow with time. And in fact, you do get them. You get some effects that grow like logarithm of A, and also some effects that grow at large physical distance too. And also notice that the gravitational slip is non-zero. Finally, let's notice that all of these effects have the property that they break down when we're at large time, that is when A is very big, or when we're at large spatial distances. Okay, so perturbation theory is breaking down. Very, very interesting effect. Now let's look at what happens when you include the effect of inflationary gravitons. And first, let's look at that generically. Okay, let's look at the effect that they have on gravitational radiation. Okay, so here's what the classical part of the equation of motion looks like, and that's equal to a source, which remember is the integral of that structure function T2. Let's just examine what this would do for various dependencies of the source. So suppose that the source wound up going like a to the fourth log of a, then you would get corrections to the mode functions that grew like logarithm of a squared. Suppose instead it didn't have the logarithm, then you'd get just a single logarithm in u. And if you had a less strong dependence of the source, you'd get things that fell off, but things that fell off less rapidly than the classical effect. Okay, well, the leading parts, the most cosmologically significant parts of T2 look like this. So there's a local piece and a non-local piece. Remember, making them the strongest effect means most number of A's and H's and fewest numbers of derivatives. So that's what this looks like, and that gives a source that indeed has this effect that we look like. So both of them have the effect that we look like. That's going to give rise to a change in the mode function that actually changes the amplitude of the tensor power spectrum. So it would change it by a factor of the number of e-foldings that you wait until the end of inflation. It would grow like the number of e-foldings squared. That's certainly not resolvable now. We haven't even resolved the tree order effect. But you can imagine that that might eventually be resolved by 21 centimeter, when 21 centimeter radiation goes from being used to do astrophysics to being used to do primordial cosmology. And note again, the breakdown of perturbation theory is occurring. Okay, well, at this point, some people are also probably screaming and saying, wait a minute, you've just been calculating these quantum gravitational effects and not taking account of the fact that quantum gravity is not a renormalizable theory. How can you do that? The reason why I can do it is because these are infrared effects. I think I'm a little bit shy on time, so I won't go through the details, but suffice it to say that when you go through and legitimately do all the renormalization, what you're left with is something which is growing faster like a logarithm of A than any kind of correction to the counter term. And you're also left with non-local pieces that grow faster than any sort of counter term could give you. Okay, let's talk a little bit about this fascinating to me issue about what happens when perturbation theory breaks down. Because I have to tell you that even this extra dimensionful constant that you've got, h squared, is not going to save you because it gets multiplied by g, and g times h squared, even for the highest scale inflation that we might imagine, is a very small number. It's like 10 to the minus 10 or 10 to the minus 11. So it would only be by the growth of these large logarithms that we could hope to see that sort of an effect. And of course, once the one-loop logarithms get big, then the two-loop logarithms are getting big, and the three-loop and four-loop logarithms are getting big as well, and you have to put them all together. You might throw up your hands at this stage and say that it's just hopeless, but you'd be wrong about that. Our colleague Alexei Starobinsky confronted a very similar issue that occurs in scalar potential models, and he long ago developed a stochastic technique which will actually sum up the results of those things and give you reliable results for what happens at late times in those cases. It turns out that that technique doesn't quite work for quantum gravity because of the presence of derivative interactions. It also turns out that the renormalization group doesn't quite work, as I believe we've had a talk on last night. But the new idea that we have here is that you can put together a variant of the two. You can actually mix the two together and probably get a technique that will work. So it turns out that you can, the propagators have what Bryce DeWitt would call a normal part and a tail part. So for example, the key propagator looks like that. That's the normal part of the propagator. That's the tail part. And some large logarithms come from the tail part. For example, here, some large logarithms are associated with ultraviolet divergences. The reason why the Starobinski technique doesn't work is because of these guys. The reason the renormalization group doesn't work is because of those guys. So what do? Put the two together, distinguish between the different origins of large logarithms, and try and sum up the large ultraviolet logarithms using a variant of the renormalization group, and try and sum up the large tail logarithms using a variant of Starobinski's technique. And I think that will work. No guarantees, but I think that will work. If you do that, all of this is going to result in some sort of non-local effective action. And for example, the factors of those logarithms of A that you've seen ubiquitously occur there, those are consistent with 1 over box R. Again, I'm a little bit short on time, so I think I won't go through the details, but it's easy to show that if you act box on f of t, it takes that form. And if you then just invert that and specialize to de Sitter, where R is 12h squared, you get, in fact, -4 times that factor of logarithm of A. So those factors of logarithm of A that we see in de Sitter are consistent with 1 over box R. They don't have to be 1 over box R. There are other operators that could give them, but that's the simplest one that would give them. And interesting thing about that operator is that it builds up and freezes in. So after the end of inflation, R goes to 0 once the universe reheats, because during radiation domination, R vanishes. So what this would do is build up, then become flat, turn off, and then at very late times, after the universe experienced matter domination phase transition, it would begin to grow again. Maybe this is what's giving dark energy. Maybe also you can get a model of inflation that is just driven by a large lambda and gradually killed by the buildup of these sorts of effects. And notice also that we're getting changes in the force of gravity. Maybe at the end of all of this, after the effects have gone non-perturbative, maybe what you get is some modification of the gravitational force law. You'd expect it to be just exactly where you want it. Not at short distances, because remember, this thing is being driven by infrared gravitons that are getting ripped out of the vacuum by inflation. You'd get it at large distances, and that's where we'd like it. Finally, there is the gauge issue. So it turns out on flat space, the graviton self-energy is gauge, the graviton propagator, of course, is gauge dependent. The graviton self-energy inherits that gauge dependence, and it's probably, although not certainly, true that the leading de Sitter contributions probably also inherit this. We must eliminate that. To get reliable results, we absolutely have to eliminate that. But let's invoke a little bit of common sense here. Just because something is gauge dependent doesn't mean it's 0. There is a technique for eliminating it. I'll show you that technique. Actually, I think I'm out of time, so I won't show you that technique. But after you do eliminate it, you're going to get a non-zero result. And all that's going to happen is that the coefficients get changed a little bit. You're not going to get something that was there to just go to 0. The technique is itself very, very interesting. This is work that was done with Tomislav Prokopets and Shunpei Miao. Again, a European, Asian, American collaboration, and is being pushed forward by, also in collaboration with Dražen Glavan, who's a European physicist. The basic setup is just to short circuit Donoghue's path to low energy quantum gravitational effects. So you recall that what he does is to calculate quantum gravitational effects on flat background, although he's now switching to cosmology. What he does is to calculate an S matrix element, which is gauge independent, and then use inverse scattering to infer the exchange potential. He will compute amplitudes, of course, in Fourier momentum space and isolate the non-local, non-analytic contributions that give the biggest effect. Our variation is just to view the amplitudes as correcting the effective field equations directly without going through the issue of calculating the amplitude in Fourier space. We work locally in position space. We isolate the same non-local, non-analytic contributions, and that makes the amplitudes resemble the effective field equations. And the key identities there are that the massive particle that you would be scattering times the massless particles that are occurring that are of interest to you, can, using a set of identities that Donoghue derived that capture this non-local, non-analytic effect, they just become local, and that reduces the diagram to a form that it can just be viewed as a correction to the effective field equations. For example, this kind of a diagram right here, where you're scattering two massive particles and you're looking at the quantum gravitational correction to a massless scalar exchange potential. If you use the Donoghue identity, that sets these two things to a delta function and closes it up so that you've got something that could be viewed just as a correction to the graviton self-energy. And lo and behold, when you work this out in terms of the most general covariant gauge in flat space and calculate the corrections to the corrections that depend on the two gauge parameters, A, the factor in front of the gauge fixing functional, and B, the factor on the trace part, what you get is that all the gauge dependent parts just add up to zero. And just as I claimed, all you do is to change the coefficient of the thing, but you do get a gauge independent and non-zero result. Okay, well, that brings me to the end of time and also brings me to the end of my talk, so I'll just conclude at this stage. Graviton self-energy quantum corrects the linearized Einstein equation, and that's the thing that you want to study in order to look at how inflationary gravitons will change both the propagation of other gravitons and will change the force of gravity. The strength of the effects depends on the occupation number. In flat space, the occupation number is zero. All you get is quantum vacuum fluctuations, and that's why not much happens. Nothing at all happens to the graviton mode function, and there are only short distance, very short distance corrections to the gravitational potentials. During inflation, the occupation number grows like a bat out of hell. It grows exponentially rapidly. It's an infrared effect, which is, by the way, good. That means that you can use it reliably, even though it's a quantum gravitational effect. And that means that you get large distance and late time growth. And I've exhibited that for you. Graviton contributions are more complicated and also more interesting than those from matter. So, for example, matter contributions to the graviton self-energy only involve 4 structure functions. Graviton contributions involve 9. Even on flat space, that's true. The counting is 2 versus 3. They're also stronger. For example, even in cosmology, there's no contribution, no correction to the mode functions at one loop from a loop of massless minimally coupled scalars. But there is a correction which grows, which actually changes the amplitude of the tensor power spectrum from inflationary gravitons. These kinds of corrections induce large space and large time logarithms, which cause the breakdown of perturbation theory. And no promises, but I think that you can sum the tail logarithms using the Starobinsky formalism and the ultraviolet logarithms using a variant of the renormalization group. And that's going to give you some sort of non-local effective action, and it likely gives modified gravity even at late times, which is itself a fascinating topic. It means that we can go from just shooting in the dark and guessing, maybe this is an interesting model of modified gravity, to actually deriving it. Much work is needed to eliminate the gauge dependence problem, and the basic idea is to use the Donoghue identities to view the amplitude as a modification of the self-energy. I've shown that that can be done, or rather Tomaslov and Schunpe and I showed that that could be done in flat space. We're right now working on how to do it in de Sitter space, and I anticipate a positive outcome. I also anticipate that this is not going to cause the results that we're getting here to go to zero. All it's going to do is to change the numerical coefficients. So thanks very much for your attention. That's it.
Thank you. Well, I already have some couple of people who are raising hands. Alexei, first.
Okay. Thank you, Robert, for this very interesting talk. My general remark is that in this problem, one should distinguish between two cases. So, which figure you are actually considering? Either you considering some viable cosmological model, inflationary model, say driven either by scalar field or, as in my model, by r plus r squared, in which the stage is only metastable. And the second case, if you really consider Einstein gravity with a cosmological constant. In the first case, scalar perturbations are always larger than tensor one, and this breaking of the perturbative expansion actually occurs much earlier and not due to gravitons, but due to scalar degree of freedom, and this breaking of perturbative figure simply means that you cannot consider the background as an exact de Sitter. In fact, you have to consider all effects not on the de Sitter background, but on the de Sitter background with large scalar inhomogeneity at very large scales. In the second case, which is different indeed, in which you have Einstein gravity with an exact cosmological constant. Well, for me, it's a little bit academic problem, but still, in this case, you indeed don't have large scalar perturbations. You have only gravitons. But then, okay, this problem, the asymptotic behavior of Einstein, quantum Einstein gravity with the cosmological constant is an, I agree that it's an open question. But once more, my general remark that it is nothing bad in the breaking of the perturbative expansion, because indeed, as you said yourself, it's infrared effect, and this simply means that one cannot consider the exact de Sitter as a background, and we have a well-known result from a classical Einstein gravity with the cosmological constant. The statement is that exact de Sitter is not the unique late time attractor, as was shown in my 1983 paper. Actually, the generic late time attractor of a classical theory is only locally de Sitter, but globally it is very different, and may even have much more complicated spatial topology.
Well, thank you for those comments with which I agree.
Okay.
Okay, thank you. And Kostas?
Yeah, hi. Thanks for this nice talk. I have a couple of technical questions. So the first one is, why you didn't consider ghost loops?
I did.
I didn't see them. Oh, you mean the results include ghost loops?
Oh, absolutely, sure. Sure. You see that dashed line there? That's a ghost.
I see. Actually, that's my second question is exactly on this slide. So in the first line, where you use the fact that the matter stress energy tensor is conserved. So the right-hand side should have been a local function. So why are you using 0 or are you using a delta function on the right-hand side?
Well, let's see. So the classical part should be 0. The one loop part, or the classical part, should be a delta function. The right-hand side should be just 0, right?
When you have a classical identity, then when you put it inside correlator, that becomes a local. So the Ward identity will have a right-hand side with a delta function. And
well, I think if you work that through, you'll see that that's making a classical, that is present, so absolutely present, and we have checked that that's there, but that's occurring in the tree amplitude.
Okay, so if you say you checked it, I mean, I would have expected the relation between the T's and the R's at this stage. Some of the T's to be related to some of the R's. The R's would have appeared on the right-hand side. But okay, I guess I have to see your paper. And the final is a more general question. Why are you working position space rather than momentum space on the spatial coordinates?
Because of cosmology, right?
On the spatial coordinates, just the spatial coordinates.
Yeah, so the translation is not a good symmetry, so it's not a good idea to take
it is on the spatial coordinates.
Transforms.
It is on the spatial. It is on the spatial coordinates.
You could, if you wish to, but it turns out to be a little bit more effective for us to work locally in space as well as in time. You can see that if you Fourier transform in space, then that's going to give rise to issues about whether or not you could actually do this sort of experiment. Right, because a spatial Fourier transform is taking an integral over all space and including a lot of things. The sort of primitive thing is the position space version of it.
But that separates more clearly in the UV issues from IR issues, which is some of the things you want to separate.
Well, it's already pretty clear. I think it's already pretty clear how to separate ultraviolet from infrared effects. So I think you can already make a pretty good separation of that. Renormalization is not in any doubt about these theories. And it turns out many people, when they first start working in these backgrounds, have the same belief that we ought to spatially Fourier transform. The longer you do it, the more the greater the tendency is, I think anyway, at least I found in my own work, let me not speak for everybody else, I found the greater tendency was to keep everything local in position space. But look, let 100 flowers bloom. The calculations are the same calculations.
Sure. Thank you.
Okay. We have 1 more minute, maybe for a short question or any comment. If there are no further questions or comments, then let's thank Richard again.